Again?
All right, so chapter 6. I'm going to take the stopper here and I'm going to sling it around my head, and then I'm going to let go. But not yet. We need to make sure it's safe. So, actually, I already have a mark right there. I'm going to stand right over here, and I want to swing it so I hit right there. Or somewhere along this line right here. So I'm going to try to hit this spot right here. So as I stand here, and I swing this around my head, the question is, where do I let go so that it hits that spot? So let me draw up an absolutely spectacular model of the room. So if that's my target right there, and I am swinging it around like this, and I guess from an overhead point of view, that would be counterclockwise. Where do I release it in order to hit that spot right there? Now, you're going to tell me where to release it, and just for the sake of ease and communication, let's just, like a clock, that's 12, 3 o'clock, 6 o'clock, 9 o'clock. Now, I have some control over releasing it. If somebody says release it at 6 o'clock and someone else says release it at 6:01, I really can't differentiate between those two. I probably can do half-hour increments, maybe a 15-minute increment if I'm feeling saucy, but that's probably as fine-tuned as I can get with my release. So, where? Speculate. Where do I release it?
Around 3 o'clock.
Around 3 o'clock. All right, so somewhere around there. Anyone else? About 2? Put it closer around there. Any other one?
I want to say closer to 6. And I would think closer to 6 because if you're doing it at 3, then it's going to want to continue to go around more with.
So if I release it here, so you're picturing release it at this point, and it's going to curve around like that. That's what the impression of what you just said.
Yeah.
Okay. And I guess the 2 o'clock and the 3 o'clock, you're speculating it's when I release it.
When you let go, it's just gonna stay
In a straight line.
yeah.
It, regardless, this is an overhead point of view. It will curve down. I can't control the force due to gravity. It will go down some. But it sounds like you two have similar thinking. It's just a matter of where I'm actually physically standing in relation to the target. That it's going to make a difference between 2 and 3. That's the impression I'm getting from what you two have said. Is that fair? You're not sure? All right, so anyone else before I release the Kraken?
I kind of want to say 12, but I can't really explain why.
But your gut says
12.
right there, somewhere around there?
Yeah.
Just for the sake of argument, I'm gonna say 1.
All right, so we've got this range here, and Brandon sort of being left out of, let those 6 o'clock people hang out by themselves.
I want to explain better, but I don't know how to physics words what I want to say.
So momentum will take it?
I feel like because it's wanting to go around, if you release at 6, the momentum is going to want to keep carrying it around and project it towards your target.
Okay, all right, so let's find out what's actually gonna happen here. I'm gonna start out with 12. and, I have some control, but not 100%. Yeah, so Madison, you might wanna move that way. Jacob, you're a little bit safer, I think, than Madison, however, and James, I think you're probably fine. I do want to, say that when that year I taught middle school, I was doing this, and I did not hit Scott. I just wanna put that out there, I did not hit Scott. I got closer to Scott than I thought I was going to, but I didn't actually hit him. Scott was prone to exaggeration, his mom knew it. Everyone knew that Scott was prone to exaggeration.
Poor Scott.
But that was, yeah, I was a great guy, but, you know, a bit overzealous in some of his descriptions. So that was first period, I almost hit Scott, but didn't hit him. Last period rolls around and students come in and say, "Hey, Dr. Fox, I heard you hit Scott this morning." No, I did not hit Scott.
Why not, Scott? Anything breakable?
My first year here, my 151 class was in a biology room, and there was glassware everywhere. It makes us a lot more nervous when we do this bit. All right, so I'm gonna release it. I'm sort of standing right in front of the X there. It's a little bit off of my drawing, I guess, closer to my drawing, it'll be more like here. All right, so I'm gonna release it when it's at this spot right here. Try to center it on my head. 3, 2, 1, go. Did it look like I messed up in my release? Did it look like it, or did it look like I released it about the right spot?
Good.
All right. So which way did it go when I let go?
Left.
All right, so Brandon. You good with my releasing it at 6?
Yes. Oh. No.
You know, it's a question of, you know, academic integrity versus I really don't care about other people. So what do you think's gonna happen? If I release it here, what do you think's gonna happen to it? Yeah, it's gonna go that way. And I would clear you out before I actually did something like that. Unless Scott were here, I could pay back, but. I would never take it out on a student. Never. That's why I have dogs. No. That sounds even worse. I was watching an episode of Hawaii Five-0, the original series, and I think it was the Chinese had infiltrated a base, and the episode starts out with dogs and men lying around everywhere. All the men were killed, but they made a special point to say none of the dogs were harmed. The dogs were knocked out. I always thought that was strange. Humans, whatever, but don't hurt the dogs.
Hawaii 5-0.
Censorship of the 60s or early 70s.
I was getting ready to say, me and you may be the only one that knows what that is.
Seems a new one, but.
Oh, that's right, I haven't actually done the trying to hit the target bit. I got sidetracked. All right, so now I'm gonna try to hit the target. Thank you. And so I'm gonna try to release it somewhere between 2 and 3. I'm gonna give a little bit more speed, hoping that it'll actually hit the wall before it hits the floor. 3, 2, 1, go. A little bit overzealous there, but. So the question is why? Why does it go straight when I release it? Well, it's circular motion before I release it, but once I release it, it seems to just shoot off at a tangent.
Because you holding the string, it's almost like it's orbiting around your finger, and as soon as there's no connection, it's just gonna go in a straight line.
And that's actually a concept from chapter 4 or 5. What is that concept known as? I don't know if I ever explicitly stated it, but,
In your motion.
well, yeah, that's true.
But not what you're looking for.
No, not what I was looking for.
Orbital motion.
That would explain why it's going around in circles, but when I release it, why it would not. Alright. Have I talked about inertia girl in this group?
No.
Alright, that was the nickname that my wife and I had for our daughter. And I do have my daughter's permission to tell the story. She was fine with my telling the story, except when she was actually in the class, and then she did not want me telling the story. At this point, she's old enough, she's married out on her own. When she was young, there'd be an example, need to go to the store. She's too young to leave in the house by herself. So, say it's time to go, she doesn't want to leave. You know, not a real shock at some point. But manage her, drag her to the car, whatever it is, get her to the car, we get to the store, she doesn't want to get out of the car. Get her into the store, it's time to leave, she doesn't want to leave the store. Get her to the car, get her home, she doesn't want to get out of the car in order to go into the house. So it's not a matter that she wanted to be playing in the house, it's a matter that she just wanted to keep doing whatever she was doing. That's the concept of inertia. Inertia is the tendency of an object to want to keep doing whatever it is doing. It is not laziness. It is a stubbornness. There's another textbook that says, it's another word for laziness, and I'm thinking, no. If you're digging a latrine ditch, if you're lazy, you want to stop digging. Inertia would indicate that you want to keep digging once you started. Now, getting you started is a difficult matter, but once you get started, you want to keep doing it. So objects want to keep doing whatever they're doing. So at the moment that I let go, at that moment, it is traveling in that direction. And now it wants to keep doing that. And in order to stop, something has to make it stop. So that's why the gravitational force is still acting on it, so that's why it curves downwards. But it will go in a straight line until it hits the wall or the floor. We can also look at that from the fourth point of view, that force is mass times acceleration. Acceleration is the change in velocity over the change in time. So if my velocity changes, there must be a force to do it. So while I'm swinging this thing in a circle, the velocity is changing because the direction is constantly changing. Because the velocity is changing, there has to be a force causing it, and that force is that force that's basically from the string. It's the tension in the string in the case of what I was doing just then. So now, since there is an acceleration for something traveling in a circle, let's come up with an equation for acceleration. We'll do somewhere down there. So let's say this is the center of the circle. And it's traveling clockwise. So at this point right here, it is traveling in that direction at some velocity. We'll just call it v sub I. This angle right here, I'm gonna call phi. And then, at this point right here, this is some final velocity at some angle phi. Now I am going to assume that the speed is constant, that my initial speed equals my final speed. My velocities aren't the same because the direction is different, but the speeds are the same. And what I want to do is figure out what is the acceleration. not changing acceleration, acceleration equals. All right, well, I know acceleration is change in velocity over change in time. So acceleration equals change in velocity over change in time. And change in velocity is final velocity minus my initial velocity, because change is always final minus initial. Over time. All right, so let's try to figure out velocities here. I know that the velocity is tangent to the path, so that is a right angle there, that is a right angle there. Now a little bit of geometry, a little bit of trig. But first, a dramatic pause to see, are there any questions?
What did you say the angle was called? Did you say phi?
Phi.
Okay.
Yep. Phi. It looks a lot like the zeros I sometimes do, except the stem is longer. I usually use theta here, but I'm going to use theta for something else in a moment. And it's just a lot simpler to use a different Greek letter. All right. I'm going to break this up into horizontal and vertical components. I hat and J hat. So I'm breaking my velocity up here. Sort of extend that. So that is a right angle there. Just looking at the horizontal component of velocity. If this angle here is phi and that is a right angle, what is this angle right here that I just arced in blue? Or if you need something more concrete, if phi is a 30-degree angle, what is this angle up here?
60 degrees.
All right, so in general, if that's phi, what is this right here?
Down there.
You said, say it again? You said negative? I'm looking for something in terms of phi. All right, if phi is 20 degrees, what is the angle up here?
So it's 90 subtract, 180 subtract 90 subtract that one. Give you that one.
All right, the angles in a triangle add up to
180.
180 degrees, so it's 180 minus 90 minus phi is equal to that, or just 90 minus phi.
Yep.
90 degrees minus phi, which I'm just going to label as phi prime. So I know that this angle right here that I've arced in blue to be the complement of phi. Then what is this angle right here? That I've arced in whatever color this is. Purplish. Did you say phi? It is indeed phi. This angle and that angle are the same. So what I am doing here is I'm breaking my velocity up, which is over to the side here. I have a velocity. This angle here is not theta, it's phi. So what is the horizontal component? this is M and N. That's a right triangle, doing right triangle trick here. How would you find this length?
Would it be velocity times cosine of phi?
Which trig function?
Cosine.
Cosine, yeah. Technically, velocity has the direction, we're just looking at a magnitude here. So it is indeed v cosine of phi, and this would be v sine of phi. So my initial velocity is whatever my speed is. Since speed is constant, we'll just drop a subscript there. V cosine phi I hat plus V sine phi j hat. Well, I need some more room over here. If I break my final velocity up, it is exactly the same logic here. It's going to turn out that this angle here is phi. And so this will be V cosine I hat, V cosine phi I hat minus V sine phi j hat. Divided by however much time it takes to get from that point 1 to point 2. And what does that simplify into?
What is that over? You said time?
Over time, yeah, however much time it takes for the object to get from here to here. So what does the numerator simplify into? All right, we'll do the intermediate step. Let's distribute the negative sign. What does the numerator become if we distribute that negative sign? That negative sign. Oh, over there. So we have V cosine phi I hat minus V sine phi j hat, that's just that, minus V cosine phi I hat V sine phi j hat over time. Okay. Now what does the numerator become?
You can cancel out your, I-hats.
Yes, you can. So that and that cancel, and what do I end up with then?
2 times V sine theta or
Phi.
phi j hat divided by time.
All right, one small issue,
Negative.
negative. Don't forget that negative is critical here. It tells us the direction of the acceleration. It's in the negative j hat direction. Since this is sort of my central point here, my acceleration is going to be in the negative j hat direction, which is down. All right, so I have this right here. I want to find the acceleration at the very peak. So we need to sort of take it to a next step here. I'm going to take the negative j hat and I'm just going to put it off to the side. So that means this is equal to 2v sine phi over time, negative j hat, and they do have that in parentheses because otherwise I'm just subtracting j hat, which is wrong. This piece right here without the negative j hat is the magnitude of the acceleration. I guess technically written that way, which I'm just going to use as a for right now. So I need to simplify that 2v sine phi over time. All right. So I have part of a circle here. I have some radius of a circle. If I have some angle down here, theta, and a radius of a circle being r, what is this length right here? Or what is the relationship between this length r and theta? All right. What is the circumference of a circle?
Pi.
Oh, you're stopping at pi? There's more, pi is definitely in there.
Is pi r squared?
That's the area, it's the other one.
Oh.
2 pi r, there we go, all right. So if I do an entire circle, I know that the distance all the way around, the arc length of an entire circle is 2 pi r. What is the angle if I go all the way around? Somebody say it, I missed it.
360 or 0, depending on which one you want.
Going all the way around, so 360
Degrees.
degrees, yeah. How many radians is that? More than 2. There we go, 2 pi radians. What is a radian? Have I done the radian bit yet? I'm assuming some of you would have done it already from pre-cal, but, or geometry. What is a radian, besides a unit of an angle? Why are there 360 degrees in a full circle? Who's to blame? Babylonians actually are to blame. Over there. All right, so the Babylonians had they realized that 60 was a special number. They also realized that perfect shapes were special as well. So if I have an equilateral triangle here, and they combine the two, so I have this perfect shape of 3 sides of equal size and 3 angles that are equal, and if I make each of these 60, that gives for a triangle 180 what we now call degrees, to add up the angles. So I have a wedge here that's, each side is 60. If I take that and I tack on another one here, and another one there, and another one there, and another one there, and another one there, I can actually get it to go all the way around. If all my triangles are equilateral and the same size, I can pack 6 of them in there. And so, that's where 360 comes from. Now, there have been movements in mathematics, they look at that and they go, well, the 360 is completely arbitrary. I mean, if 50 had been a special number to the Babylonians, we'd be talking about 300 degrees in a circle instead of 360. And so there was a huge movement, especially in, I think it was the 19th century, I think French were the leaders in it at the time, of trying to eliminate as much of man from math as possible. They wanted to come down to what is actually just true by nature of the universe. And they thought about circles and they said to themselves, well, there's something true about all circles. All circles have a radius. So if I take a circle with some radius r, and then I take that length there, so imagine I got a piece of string here and I wrap it around, so that my arc length here is r, and that this is r. This angle right here is the same, no matter what circle it is. If I take its radius and I wrap it around the side, I always get the same angle. And that angle is 1 radian. And so now the question is how many of these radiuses can I fit around the outside? Well, I get 2 pi radiuses around the outside. And therefore there's 2 pi radians on the inside. And so the relationship is that arc length, back over here, if I label this S, the arc length is just equal to the radius times the angle, if the angle is in radians. So if I'm doing the entire